Hello, this week we are going to be studying waves. In the coming weeks, we'll learn about how waves manifest themselves in the form of sound and light. But this week, we're going to look at waves in general. This video will look at what waves are, some cool things that they can do, and then we'll finish up with some ideas of what you can make observations about and what you can do for your weekly lab. Waves can do two things. The first thing that they do is they carry information about a disturbance. So for example, this trout that's on the other end of my fishing line here is going to cause a disturbance in the fishing line, and that's going to send information to me over here about that disturbance. Because I felt a disturbance in the line, I know that there's a fish on the other end. The second thing that waves can do is that they can transfer energy or information without transferring any sort of matter. The fish didn't need to send me a letter to tell me that it was on the end of my line. The fish could just transfer energy through waves to me without having to do that. So because the fish caused a disturbance in the medium, and that disturbance transferred in the form of energy to me. Maybe both the fish and I agreed on that one wave pulse means that the fish is on the line, and that information was successfully transferred. There are two types of waves. The first type is what's called a transverse wave, and the second type is called a longitudinal wave. This is a GIF showing how they manifest themselves in a slinky. For a transverse wave on a slinky, you would move the slinky up and down to send a wave pulse down, and in a longitudinal wave, you'd push the slinky back and forth. Let's look at how these two waves differ on a fundamental level. Let's start with a longitudinal wave. In a longitudinal wave, the wave moves to the right, but the particle itself moves back and forth parallel to the direction that the wave is moving. An example of a longitudinal wave is sound. In a transverse wave, you can see that the wave is moving to the right again, but this time, the particles that make up the medium are moving up and down or perpendicular to the direction that the wave is moving. An example of a transverse wave is light. Some of you may be wondering about water waves. Water waves actually combine the behavior of both longitudinal and transverse waves. When you combine vertical and horizontal motion together in a uniform way, what you get is circular motion. So water waves are actually a combination of longitudinal and transverse, and what you get on the surface here is the particles actually moving in a circle. The further down you go into the body of water, the smaller those circles become. Of course, this isn't the case when the wave reaches the shore. Different physics happens there. Waves can do neat tricks. The first thing that waves can do is that waves can bounce. If a wave encounters an obstacle, it can reflect off of that obstacle. This GIF here shows a wave pulse on a string meeting a barrier and the wave changing direction and moving the other way. The second thing waves can do is that they can exist in the same place at the same time, which is not something that matter can do. When waves exist in the same place at the same time, they can either add to each other or they can cancel each other out. In this GIF here, the two waves are adding to each other. Let's say the large wave pulse is 2 units high and the small one is 1 unit high. When they combine, their combined height will be 3 units tall. Also notice how the waves travel through each other. They do not bounce off of each other. Waves, the third thing that waves can do is that they can create what's called a standing wave. And standing waves happen when waves not only bounce back, but also interfere with themselves. There's a good GIF right here. This first GIF right here shows an incoming wave pulse that wave is going to bounce back and it's going to interfere, it's going to add and subtract to itself and create what's called a standing wave. This big GIF over here shows the two separate waves moving past each other, and this bottom wave down here is the addition of those two waves. You can see that when the standing wave is created, there are areas where the string doesn't move at all, and there are areas where the string moves at a maximum displacement. You can have different modes of standing waves. This first mode is called the fundamental frequency. After that, you can get the second harmonic, the third, the fourth, the fifth, all the way up. Here's a demonstration of how we can actually make those waves on an elastic cord. In this case, I'm using my headphone cord plugged into my amp. The fundamental standing wave looks like this. There is one wave peak, and it moves back and forth. If I were to double that frequency, I can get the second harmonic standing wave. There it is right there. And of course, I can keep building on those frequencies and get I can increase the frequency and get other resonant frequencies of this medium. Looks like that's 4. The fourth cool thing that waves can do is that they can bend around corners. Here is a top-down view of a wave. The wave fronts are coming in and they're encountering an obstacle. When the waves pass through this small slit, they don't go out in a straight line. They actually bend around the corners. If you have a couple slits, some interesting things happen where you have the waves adding to themselves in some places and the waves subtracting from themselves in other places. This has more applications in sound and light, and we'll look at this phenomenon when we study those units. Let's talk about different ways that waves can be measured. So what we have here in this top GIF is a wave on a string. And what this white bar here is doing is it's tracking a particular point on that string. Remember, with waves, the actual material isn't moving down the string. It's the energy or the wave that's moving down the string. The particles themselves, in this case, in this transverse wave, is only moving up and down. And there are two ways that we can represent this. We can represent this on an amplitude versus time graph, meaning we're going to track how that particle moves through space as time moves on. Or we can take a snapshot of the physical wave, and that can tell us some information about the wave as well. So here we have two graphs, a amplitude versus distance graph, and of course, an amplitude versus time graph. Let's look at some different things that we can measure, that you can measure in your lab about waves. The first thing to measure is the amplitude, and that's the distance from the resting position. If there was no wave on the string right now, it would follow this equilibrium line through the center. But as soon as we send a wave through it, the amplitude can be measured from the distance from that equilibrium line. The wavelength is the distance from one peak to the next. Or in other words, the distance between a repeated motion. So here the string was flicked up, and here the string was flicked up, and the distance between those two peaks is the wavelength. You could also do trough to trough, or you could do where it crosses over the equilibrium line. But you have to be careful with that one. If I wanted to measure the wavelength from here, it would be crossing over and going up, so I'd have to follow that and see where it happens again, which is right here. So one wavelength would be from the start to right here. We can also measure the period of a wave. The period is the time it takes for a piece of the medium to repeat its motion once. Remember that this is this is a representation of a particle moving as a function of time. So a particle is here, and then a little bit later on, the particle is here. The distance, or I guess the time between those two peaks is the period of the wave. Again, that's the time it takes for the medium to repeat its motion once. The frequency is just the inverse of the period, and that's the number of times per second a piece of the medium repeats its motion. If we multiply the frequency by the wavelength, we can get the wave velocity. That's not how fast the particle is moving, that's how fast the actual wave pulse is moving. So let's talk about some ideas for observations and some questions you could ask to inform your lab. The first tip for you is that you may have to interact with your environment to create disturbances to study. My headphone cable down there, if I just leave it there, it's not going to create any waves. I had to go interact with it to study the waves. Slinkies, stretchy tubing, or tubs of water, including ponds and lakes, are all really good places for waves to exist. Think about geese swimming on a pond or disturbing water waves, something like that. And the easiest thing, thinking about your lab, the easiest thing to actually measure about a disturbance, if you're causing that, is the frequency at which you disturb the medium. So for example, let's say I'm setting up the fundamental standing wave. I could measure the frequency of this standing wave. I'm going to count the number of cycles in 10 seconds. So let me get a standing wave going here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So let's just say it did 10 cycles in 5 seconds. 10 cycles in 5 seconds would be a frequency of 2 hertz. You could also do that with a tub of water. If you disturb the water at a certain frequency, you can measure the frequency and the wavelength and get the velocity of the wave. Some possible questions, or some outlines of possible questions you could ask. What is the relationship between property 1 and property 2? If we go back and look at the different things that we can measure about waves, you might ask, what is the relationship between the frequency and the wavelength? We know that that's the velocity. You could do a lab based on that. What is the relationship between the amplitude and the period? Meaning, if I drive this at a small amplitude, how does that change the period if I drive it at a large amplitude? You could do a lab based on that. So think about the relationship between different variables and how you can figure out what that relationship might be. And you could also think about how does some property of the medium affect its wave velocity. Maybe you want to study the wave velocity in different mediums. Maybe you want to look at what is the wave velocity through water, what is the wave velocity through a slinky. You can compare things like that as well. If you have any questions about making observations about waves or what you should do for your lab, you can always email me or visit me during office hours.